On the surface, the ship is barely moving, a few hundred meters an hour, crawling across the ocean. But underneath it, something extraordinary is happening. Steel pipe is being welded together, joint by joint, and lowered continuously to the seabed below. The ship never stops. The welding never stops. And by the time this vessel leaves, a steel pipeline hundreds of kilometers long will be lying on the ocean floor, installed with a precision measured in centimeters. This is pipelay, and it is one of the most continuous, demanding, and least understood operations in offshore construction. Let's start with the pipe itself, because everything depends on it. Offshore pipeline pipe is manufactured to extraordinary specifications. The steel must withstand not just the internal pressure of the oil or gas it carries, which can be enormous, but also the external pressure of the surrounding water column, the corrosive saltwater environment, and the mechanical stresses of installation. Pipe used offshore is typically coated in multiple layers: a fusion-bonded epoxy layer for corrosion protection, a field joint coating, and in many cases, a thick layer of concrete weight coating, a dense concrete shell wrapped around the outside, which adds enough negative buoyancy to keep the pipe firmly on the seabed and protects it from mechanical damage. A single joint of 12-inch diameter concrete-coated pipe, about 12 meters long, can weigh close to 2 tons. There are several methods for installing subsea pipelines, and each suits different water depths, seabed conditions, and pipe diameters. But the most widely used, and perhaps the most visually dramatic, is S-lay. In S-lay, the pipe is built up on a long fabrication ramp called a stinger, which projects from the stern of the vessel at an angle into the water. Pipe joints are welded together on this ramp in an assembly line, each joint added to the growing pipe string, welded, inspected, coated, and then allowed to slide down the stinger as the vessel moves forward. As the pipe enters the water, it forms a gentle S-curve, angling downward from the stinger, then curving to become horizontal as it approaches the seabed. The shape of this curve, and the tension applied by the tensioner machines that grip the pipe on board, is critical. Too little tension and the pipe buckles. Too much and it overstresses. Managing the pipe configuration in real time is a continuous engineering calculation. On the seabed, survey teams, often using ROVs, track the pipe's position, making sure it lands on the correct route within specified tolerance of the planned alignment. For deepwater pipelines, a different method is used: J-lay. In J-lay, pipe is assembled and lowered vertically, straight down, from a tall tower on the vessel. The J-lay method creates a J shape in the water column, vertical near the surface, curving to horizontal at the seabed. This dramatically reduces the pipe stress in deep water and requires far less top tension than S-lay. Some J-lay towers are over 100 meters tall, towering above the vessel deck like an industrial crane reaching into the sky. The vessels that perform these operations are among the most sophisticated in the world. A large pipe-lay vessel can be 200 meters or more in length, fitted with dynamic positioning systems that hold the ship on location without anchors, using a network of GPS references, acoustic transponders, and computer-controlled thrusters. The lay spread on board, the combination of pipe handling equipment, welding stations, and tensioners, is an entire industrial facility built into a ship. Some of the world's most famous pipelines were laid using exactly these methods. The Nord Stream pipelines beneath the Baltic Sea stretch over 1,200 kilometers. The Langeled pipeline carries gas from Norway to the United Kingdom across the North Sea. The Medgaz pipeline crosses the Mediterranean seabed at depths of nearly 2,200 meters, connecting Algeria directly to Spain. Pipeline installation is also inseparable from subsea construction. The preparation of the seabed, the installation of pipeline end manifolds and tie-in spools, and the burial of the pipeline where it crosses shipping lanes or areas of seabed movement. Trenching vessels cut channels in the seabed and allow the pipeline to be buried for protection. Divers and ROVs perform the final connections at the seabed, joining pipeline sections to subsea structures with a precision that seems impossible given the conditions. When a pipeline is complete, it is pressure tested, dewatered, and commissioned, a process that takes weeks and involves thousands of checks before the first oil or gas is allowed to flow. The result of all this effort is invisible to almost everyone: A pipeline on the ocean floor carries no lights. It has no crew. It makes no noise. It simply sits there, year after year, carrying energy across distances that would take weeks to walk. It is one of the most reliable, most essential, and least visible pieces of industrial infrastructure on Earth. The pipe was laid, the weld holds, and somewhere beneath the ocean, the energy flows.